Hi, so today I want to talk to you about the weight equation that we've been using since Chapter 5. And in Chapter 5 we talked about the weight, which I also said could be called the force of gravity. F sub g is what I like using. A lot of books will use a W with the vector harpoon over it. And I said the force of gravity is the mass times the strength of gravity. Only usually I didn't put an arrow over g, I just had g without the arrow, and I said the direction was the minus y direction, straight down. Well, what we're really dealing with this equation is our first example of what we in physics call a field equation. And with the fundamental forces, all of the fundamental forces of physics can be understood through the concept of a field. An imaginary seeming structure that surrounds an object that is responsible for creating the fundamental forces, where if you bring a like object into that existing field, you get a force interaction. Electricity does the same thing, magnetism does the same thing. All of the fundamental forces can be described through a field representation. So what we're saying here is that G, with an arrow over top, is the strength of the local gravity field that's being created by the masses that already happen to be there. So when we're normally talking about Earth, or being near Earth, well, there's a giant massive object, Earth, and usually we're a pretty fixed distance away from it, the radius of Earth, which isn't constant, but it's on average roughly 6.37 times 10 to the 6 meters. And the mass of Earth is about 5.98 times 10 to the 24 kilograms. So what we would see by setting the true force of gravity from Newton's, and I say true, the better force of gravity, Newton's theory of gravity, minus the universal gravity constant of 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared, times the mass of one object times the mass of the other object, divided by the distance between them squared, equal to our weight field equation. Well, one of those masses is just the mass of the object we brought into that gravity field. So the gravity field then would just have to be equal to the universal gravity constant times the mass of the object creating the gravity field divided by our distance away from that object squared in the minus r hat direction, directly in towards the center of that massive object. So for Earth, the strength of gravity on Earth, or near Earth, is going to be minus the universal gravity constant times the mass of Earth, and then to account for our distance away from the center of Earth, it would be the radius of Earth to take us to the surface plus our height above the surface of Earth squared. Now, at sea level, that height is 0, so if I plug in the universal gravity constant, the mass of Earth, and divide by the radius of Earth squared, we get the value for gravity at sea level at the North Pole of 9.83 meters per second squared. Thanks for watching.